Okay, so last week we learned about how your computer can make simple decisions based on whether some criteria is true or false. And while that's not exactly artificial intelligence, it is pretty cool. Today we're going to be talking about something even cooler. This week we're going to use a similar tool that will open up a world of possibilities so large you might just spend the rest of your life discovering them. Computer science, the golden arena of endless well-paying jobs, needs problem solvers from all backgrounds, but appears surrounded by a thick wall of incomprehensible ones and zeros, self-righteous nerd minions, and endless differential equation nightmares. This video textbook attempts to create an entrance through that wall by teaching programming basics in the language of real people. This video is a lecture covering programming tools and methods. To watch a real-life example in 3 different coding languages, click here. And to listen to this chapter's lecture on computer science beyond programming, click here. So loops might just be my favorite programming tool. I'm sorry about that if statements, but I'm okay making decisions. I'm not good with repetitive tasks, and loops just make those a lot easier. They're certainly one of the most important developments in computer science. And interestingly enough, they're called loops because in the early days of computer science you could actually take a set of instructions on a reel of punch tape and fasten the ends together so that the computer would keep running the instructions in a loop. How's that for ingenuity? And while the punch tape is now gone, there really isn't much difference between loops back then and loops in programming today. Loops are just a set of instructions that run a code block over multiple times. For a slightly impractical example, let's pretend that you wanted to create a program that displayed all the numbers from 0 to 100 onto the console. I don't know why you'd want to do that unless it's part of a homework assignment. But if it's part of a homework assignment, you'll thank me later. So one way to do it is to just write all those output statements yourself. Or you can use a loop and make the computer do some of the work for you. In a loop, everything inside these curly brackets will run over and over again. Now of course it takes more than just curly brackets to make a loop, but we'll talk about that in just a minute. So to start, let's go ahead and create a variable and name it number. We're going to put in the value 0. Or in other words, we're going to allocate a slot on the memory shelves big enough to store an integer. And we're going to name that spot, or the access to that spot, number. Then we're going to use the assignment operator to reset all the bits at our new memory location to store the value 0 as an integer. Hopefully all that made sense to you at this point. If not, it might be a good idea to go back and watch our video about variables in the memory warehouse. Okay, let's go back to talking about loops. Now inside our loop, let's display the value being stored in number to the console. Then after that, let's add 1 to it and store the sum of those two numbers as the new value inside number. This line of code retrieves the value stored in the variable number and adds 1 to it, and then sums those two numbers and stores their value back into the variable named number. If that sounds confusing, let's just wait and watch it in the example. I think you'll pick it up pretty quick. In fact, let's go ahead and run through our full loop. Okay, so the value at number is 0, so the first time that we run through this, it displays 0 to the console. Then it takes the value in number and adds 1 to it and stores that new value back into number. Since the value at number is currently 0 and 1 plus 0 equals 1, the new value stored in number will be 1. And now that we're at the end of our loop, the program will run back to the top of the loop. Because the last value stored in number was 1, this time through the loop, 1 will be outputted to the console. Then our code adds 1 to 1 and stores that value back into number and starts the loop again. Now it outputs 2, and now adds 1 to 2 and stores that. So now we output 3, and the cycle continues automatically and indefinitely. Now, as cool as that indefinitely thing sounds, it's actually kind of a problem. If we don't provide some logical way for the computer to know when we want to exit the loop, it's going to keep counting forever. And in practical programming, that can be a real problem. We call these infinite loops. And in real programming, they lead to programs that freeze, crash, or feel like Windows Vista. I'm sorry, Windows, you should have just stuck with XP. Loops are classified by how you exit them. There are really only 2 types of loops. There are for loops and while loops. Hopefully that will make sense in just a second. For loops are counting loops. They run for a specific number of times. They actually track how many times you have looped through the loop and exit when you reach a predetermined number. Now to do that, they need 3 pieces of information: a counter, a condition, and counting instructions. First, we'll start our loop using the keyword for. Then add this information in parentheses. The first thing we need to add is the counter. This is going to be a variable that keeps track of how many times we have looped through the loop. To create this variable, we'll use the same syntax that you would to create a variable anywhere else. The only difference is that instead of putting this on its own line, we'll be putting this inside our parentheses. Now, I've been calling this counter the whole time, but it's much more common to call this new variable I for index. Normally, it's not good practice to name your variables or constants something so abbreviated. But wrong or not, the computer science world has been using I for so long that it's almost become a programming convention itself, even though it's already breaking another convention. It's also a very common convention to start your counter at 0. Now, you can break that rule if you have a really good reason to, but normally it's expected that you'll start at 0. Now, it's pretty typical to put a semicolon before we move on to the next set of instructions, which will be a condition. So we need something for our loop to check to know if it's reached the predetermined number of times. Now, you could do this lots of ways, but it's common to use the comparison operators greater than or less than to see if I has become greater than the number that we want to exit at. So if we want this loop to exit after the number 100, then we could use the condition, run this loop while I is less than 101. Now, I've got a question for you. Why would we use 101 instead of 100? We'd say 101 because we want the loop to print all the way to 100. Since 100 is equal to 100, not less than 100, when our counter gets to 100, this statement would be false, and we would exit the loop before the number 100 got outputted to the console. Now, after another semicolon, we need to tell the computer how we want it to count. We could tell it that at the end of our loop, we want to add 3 to our counter, or count backwards by 7s. Or we could simply just say count up by 1 every time that we run through this loop. And really, that's the most useful way to count. You might find other reasons to count the other ways, but for the large majority of the time, you'll just want to count up by 1. To do this, we can use a simple new operator. This is the increment operator, ++. And for those who are curious, yes, that is where C++ gets its name. If we place the ++ right after our I, it will add 1 to our count at the end of our loop. I think we should try this, but before we do, let me point out something interesting about our code. Since I is already storing the value 0, and it will be counting up by 1 every time the loop runs, it's going to be storing the same information that our variable number will. So we have 2 variables taking up 2 spots on our memory shelves, each keeping track of the exact same information. Now, that's really not a big deal on a small program like this running on a PC, and maybe at this point, if leaving it like that makes it easier for you to read your code, that's great. But it could be a big deal if your app is running on a mobile phone with little memory, or in a program that's running hundreds of thousands of these little commands at the same time, or in a micro robot where they've stripped down the memory to the bare essentials it needs to run. In those kinds of conditions, you need light code, and to get into the habit of writing simple code like that, maybe we should clean this up a little bit. Now, lucky for us, we're actually allowed to use I as a variable anywhere inside of our curly brackets. We'll talk about why you can't use it outside of the curly brackets next week when we talk about scope. But inside the curly brackets, we can do whatever we want with it. Just be careful not to change the value stored in I by reassigning it to a new value. Unless, of course, you have a reason and you know what you're doing. That is an easy way to create one of those infinite loops. Or you could just mess up the way that your loop counts and create a bug. We could clean up a whole spot on the memory shelf simply by replacing this whole line with one that says display I to the console instead. Okay, let's run this code. First, the loop creates the variable I and stores the value 0 in it. The program checks to see if the value in the variable I is less than 100. Since the value stored in I is just 0, the expression evaluates to true, and we enter our loop for our first pass. Somewhat anticlimactically, all that our code block does in this example is output I to the console. Since I is storing the value 0, 0 pops up on the console, and we move on to the next line. Now we're at the end of our loop, and it's time to increment. The value of I was 0, but now the increment operator will add 1 to that value and store it back into I. So now the value of I is 1, and we start our loop again. Now let me ask you, what do you think the computer does next? Since we are at the beginning of another pass, the loop needs to evaluate our condition again to make sure that it is still true. This time the value of I is 1. 1 is still less than 100, so the condition is true and we stay in the loop. Now what do you think happens? The code block outputs the value at I and then moves on to the next command, which is just the end of our loop. At the end of our loop, I is incremented to 2. Let's fast forward until I equals 100. Since 100 is less than 101, the condition is still true and we stay in the loop. After outputting 100 to the console, I is incremented to 101. 101 is equal to, not less than 101, and therefore our condition is false and we exit the loop. There you go. After all that, we have successfully printed all the numbers from 0 to 100 to the console. I promise you there are more practical uses to loops than that. And should you think that it might have been easier just to write all those output statements, it will only take a little tweaking of the numbers to count all the way to 1,000, or to 10,000, or to 100,000, or to infinity. I mean, you won't be around to see it, and you'll never be able to use your computer again, but whatever floats your goat. For loops work great when you or the user knows how many times they want to actually do something. They're not so great when you don't know how many times you want to run the loop. Let's pretend we've created a simple game where players try to weave a jolly lumberjack's beard through some gaps in a bunch of green columns. That's totally a practical situation. We're going to call it Floppy Beard. We're at the point of development where most of the game is done and we want to test it on some real users. Now, we are still finishing up the interface, so the testers will have to run what we do have finished from the console. Let's pretend that all the code to begin a round of our game can be executed with the command begin round. And don't worry if that seems a little confusing, we'll talk about how that's possible in coming lessons. Just for now, imagine that this line of code starts our game. Now, of course, there's no actual way to win at Floppy Beard. It's all about how far you can get. So when a player loses, we'll ask them if they want to play again. If they do, we can just run our loop again. If not, we want to exit our loop and end the program. Now in this case, a for loop wouldn't work because we have no idea how many times our user wants to play the game. In this case, we want to use a while loop. A while loop runs as long as a given condition is true, in a similar way that for loops do. But instead of the condition being tied to a counter, this condition is usually more like a logical expression. Let's look at this in our example. So at the end of each round, we're going to ask the user if they want to keep playing. So we're going to need a variable to store the user's answer. Let's just call it keep playing. Now let's get some input from the user. If the user wants to keep going, they can type Y for yes when the console asks them if they want to keep playing. Now let's use this information to make a while loop. First we'll write the word while, followed by parentheses. Since we don't have a counter, the only information we need in the parentheses is a condition that can either be true or false. Let's use the condition, run this loop while keep playing is equal to Y. As long as keep playing equals Y, then we will stay in the loop. If any other value than Y is stored in keep playing, then the condition will evaluate to false and we will exit the loop. Now there is a problem with this. The first time this runs, keep playing isn't storing a Y yet. Because we didn't set a value for keep playing to store, keep playing will either be storing a garbage value or a empty or null value, depending on the language. Since that is the case, our loop will never run because the condition will never be true. We can fix this in several ways, but for our example, let's change how our while loop checks the condition. In a while loop, you can check the condition at the beginning or the end. This configuration checks the condition first, but if we move this whole line down to the bottom of our code block and write the word do at the top, the computer will do the code block first and then continue running it while the condition is true. That way we are guaranteed to run our loop at least once. These are called do-while loops, and they're really just a variation of while loops. And just like with if statements, you can use Boolean operators, like and, or, and not operators, to make complex conditions for the loop. For example, later, when our game is finally ready to be deployed to a mobile device, we can keep it from killing the device's battery by using complex conditions like while keep playing equals y, and the device battery is greater than 5%, then run our code block. As we've already pointed out, even with all these ways to exit the loop, there's still lots of ways to make an infinite loop out of them. The most common is to write a condition that will always be true. If a condition is always true, either in a for loop or a while loop, you'll never exit. So you can just avoid a lot of pain by reading your conditions carefully. Actually, that's just good advice for life. Loops are everywhere. They're one of the reasons computers are so useful. Can you think of any repetitive tasks you'd like to automate? Is there anything in life that you can make easier just with the tools that you've learned so far? So much of what mankind has used computers for can be simply done with the tools that we've already talked about in this course. I mean, you still have a lot to learn, but we all do. You now understand the most important tools that make up the magic of programming. You already have more programming capabilities than a lot of the early computer scientists ever did with their pioneering computers. So use that capacity to do something amazing. Come practice with us in the exercise, where we're going to use loops to do some calculations for us.